All right, so chapter 17 is on thermochemistry. We're looking at how energy flows. All right, so energy transformation. One of the ways where energy changes can occur. Energy can be defined as the capacity for doing work or supplying heat. So there's a lot of different types of energy. There's light energy. Our food has stored chemical energy. We have the capacity to tap into electrical energy, heat or thermal energy, mechanical energy. So you're applying energy to a bike and it's propelling you forward. We take the chemical bonds in gasoline and allow that to power cars, so we're able to transform it. Unlike matter, energy doesn't have mass or volume, but we can really detect it because of its effects. Yes. There would be kinetic energy, potential energy, gravitational, positional energy could also be a name for potential energy. So thermochemistry looks at energy changes that occur during chemical reactions and also changes in state. So we talked about changes in state back with chapter 13. Every substance has a certain amount of energy stored inside of it, and the energy stored in the chemical bonds of a substance is referred to as chemical potential energy. The kinds of atoms and the arrangement of the atoms within that substance will determine how much energy is stored in the substance. So like when we buy gasoline, we're actually buying the stored potential energy that it contains. And then within the car's engine, we have controlled explosions of the gasoline, and they transform that potential energy stored within those bonds into a usable form, and that can be used to propel the car. Some of the energy that's transformed actually is something useful. We have movement in the car, and it's powering all of our accessories within the car, but some of it is transformed into heat, light, and noise. About 20% of the energy that is within gasoline is actually transformed into the useful work. So it's not an incredibly efficient process, but you know it does work. When we compare that to the mitochondria of the cell, and that's about an 85% efficient process. So biological organisms have a much more efficient of converting potential energy into usable energy than the things that we make. The energy that's released when a piece of wood is burned was stored in the wood as chemical potential energy. And we're able to utilize it. When we do burn wood, we want the heat and the light that's being given off. It might not be the most useful form of energy, but we apply it, we use it in that manner. Energy changes can occur as a heat transfer or as usable work, or it could be some combination of both. Within the formulas that we'll be using, heat is represented by the letter Q, and it's the amount of energy that transfers from one object to another because of a temperature difference that exists between those objects. The natural order of things is that heat will flow from a warmer object to a cooler object. And so if we have these two objects that are in constant contact, the heat will flow from the warmer object towards the cooler object until both objects are about the same temperature. So when you have a hot cup of coffee, obviously the coffee is warmer than the surroundings. It's in contact with the molecules of the air around it. And so the coffee is going to cause some of the air around it to get warmed up as it's trying to balance out the temperature change. If we have a cold soda, the surroundings are warmer, and so they're going to come in contact with the outside of this cup and try and stabilize or equalize that temperature difference. So it's always going to go from warmer to cooler. What happens to the energy during a chemical or physical process? The chemical reactions and the changes in physical state usually involve either absorbing or releasing heat. The law of conservation of energy states that in any chemical or physical process, energy cannot be created nor destroyed. In fact, it's just changing from one form to another. Whether or not it's actually in a useful form to us is based on what we're trying to get at that time, but it never completely disappears. It just might be in a form that we are not able to use. Hi. I'm like, all right, so the universe, if we want to think of two things, if we're looking at how energy is being transferred.
Interruption. High School Yearbook Club. Please be in the high school quad area now for your field trip. Again, High School Yearbook Club. Please be in the high school quad area now for your field trip. Thank you.
All right. Back to chemistry. So the universe is made up of two parts. Anytime we're looking at changes that are occurring, we can look at two perspectives. We can look at the system, which is where we're focusing our attention, and then we can look at the surroundings, which is everything else in the universe. So when we're looking at some of these energy changes, we're looking at, is energy being absorbed by the system or is energy being absorbed by the surroundings? Is heat being released into the system or is heat being released into the surroundings? We have a couple different perspectives of things. All right, so page 2. All right, page 2. During any chemical or physical process, the energy of the universe remains unchanged. So even though if we're looking at the system or we're looking at the surroundings, net change within the universe, there is no net change. The energy is transforming from one form to another, or it's moving from the surroundings to the system, or the system to the surroundings. But from a universal perspective here on Earth or within the entire galaxy, that energy has not changed. If the energy of the system increases because of a specific process, then the energy of the surroundings would have to decrease by the same amount because energy cannot be created nor destroyed. If the energy of the system decreases because of that process, then the energy of the surroundings must increase by the same amount. So the amount of energy that we had initially compared to the amount of energy that we have finally would still be the same because the energy is either given to the surroundings and the energy decreases of that system, or energy is gained from the surroundings and it goes into that system. But there is this movement between the two, and yet there is no loss of it. The direction of heat flow is given from the point of view of the system. So we're looking at, is the system gaining heat or is the system losing heat? And so we use these two words. We have endothermic and exothermic, and it's always from the perspective of what is happening to the system. So an endothermic process is one that is absorbing heat from the surroundings. So endo sounds like into. Heat is flowing into the system from its surroundings. In this perspective, it has a positive value. The value for heat is positive. The opposite of an endothermic process is an exothermic process. If you think of the word exit, it's releasing heat to the surroundings, so heat is going from the system, it's exiting and going out into the surroundings. So heat is flowing out of a system into its surroundings, and this is given a negative value, but the energy is still conserved. It is not lost. It is just transferring from one position or one object to the surroundings, or from the surroundings to the object. So we can use these positive and negative values to show the direction that the heat is traveling, but it is never truly lost. All right, so a couple of pictures of endothermic and exothermic processes. On the left-hand side, we have this guy sitting by a fire, playing on his cell phone. So he's sitting by the fire. Obviously, the fire would be warmer than him. So the heat given off by the fire is going to come towards him. And so the heat is going from the surroundings into the system. So that would be an endothermic process. This guy just got done playing soccer. So he is hotter than the surroundings. He's using evaporation as a way to cool himself, but the heat is going out into the surroundings through this evaporation process, and so that would be exothermic. The heat is trying to exit. In both cases, though, energy is conserved because it is just transferred from one object to the next. Okay, so a real-life application, even though we don't have snow very often in this valley, it does occur. On a sunny winter day, the snow on a rooftop begins to melt. As the melted water drips from the roof, it refreezes into icicles. And so we're going to look at the direction of the heat flow as the water is freezing and determine if it's an endothermic process or an exothermic process. And heat is always going to flow from a warmer object to a cooler object. An endothermic process, the heat is going into the system from the surroundings. And an exothermic process, the heat is exiting the system and going out into the surroundings. So in this situation, the system would be water. So we're looking at what is happening to water. And then the surroundings, what is the atmospheric air doing? So to determine the direction of the heat flow, in order for water to freeze, its temperature must decrease. So that means that heat is leaving the water in order for the temperature to drop enough for it to get into this solid form. And so it's flowing out of the water and into the air. And so the water is our system. So if heat is exiting the system, what type of process would that be? Would it be endothermic or exothermic? It would be exothermic. All right, next scenario here. Athletes often use instant ice packs to soothe injuries. Many of these packs use the dissociation of ammonium nitrate in water to create a cold feeling compress. So the instant cold pack, when you break that little, there's like an inner packet. When you break that inner packet, it has a reaction with the solution that is outside of it, and it causes a reaction between them, and then that process removes heat from its surroundings. So we have the dissociation of ammonium nitrate in a water solution would be endothermic because the heat is going from the surroundings into the system. So the cold pack is gaining heat as the surroundings are losing heat. So if something feels cold to your touch, then it would be endothermic. Continuing on page 3, the units for heat flow. Heat flow is measured in 2 units. We can talk about it in calories or joules. A calorie can be abbreviated as CAL, and it's the amount of heat that's needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. The word calorie, when it's written with a small c, refers to energy except for food. If you have dietary calories, you write them with a capital C, because In order to make our dietary calories not sound so scary, they're actually kilocalories. So when we say you have a 2,000 calorie diet, it's actually 2,000 kilocalories. But all of our food is measured on that kilocalorie basis. So it doesn't really matter if it's kilocalories or calories as long as we're all using the same unit of measurement. So we use calorie with a capital C to refer to the amount of energy that's stored in our food. A joule looks at, it's the SI unit for energy. And so 1 joule of heat also raises the temperature of 1 gram of pure water by a little bit different variable, 0.2390 degrees Celsius. And it's named after Mr. Joule here, who worked on the physics of work and heat, and he has some specific equations that he did. You can convert between calories and joules, knowing how much they are each equal to in temperature, like at the degrees Celsius. So 1 joule is equal to 0.2390 calories, or from the different perspective, 1 calorie is equal to 4.184 joules. Basically, those numbers are inverses of each other. If you want to convert from joules to calories, we're going to start with 35.6 joules. And then we need to put joules on the bottom and calories on the top. It really doesn't matter which conversion information we use as long as joules are on the bottom and calories on the top. We'll put 1 joule is equal to 0.2390 calories. So when it's set up like this, we're going to go 35.6 times 0.2390. Our joules cancel out, and the only label that's left would be calories. Looking at significant digits, we had 3 significant digits initially, so we're going to round our answer off. I want to prove to you that it does work no matter which conversion you use. So 35.6 joules, you don't have to write this down, it's in blue, but I just want to prove to you it does work. If we use the 4.184 joules in 1 calorie, now we're going 35.6 divided by 4.184. By the time we do significant digits, even though these numbers are off very slightly, by the time we do significant digits, either one would round to 8.51 calories. So it's just a personal preference which conversion information you want to use. All right, we'll do one more example. We'll go from calories to joules before we stop today. All right, so to go from calories to joules, we have 540 calories. And so 1 calorie is equal to 4.184 joules. We get this value a little over 2,000. Just to prove that it works either way. If you look at these numbers, yes, they are different starting at the 10th place. But if we look at significant digits, we can only have 3 significant digits. That's going to cause us to round our number off to 2,260 joules. And so either conversion information gives us that amount of joules. Right? That's where we'll stop at today. We'll pick up on number 5 tomorrow.